So, continuing from last time, we defined our interactive Turing machine, and we discussed... 1 minute, I'm going to close the door, it is loud. Thanks, Constantine. My office mate is closing the door. Okay, so we have our interactive Turing machine, and we define an execution, and the idea was that we have this initial machine. My pen is always too small to begin with. We have this initial machine I that gets some input. I call this input Z, and then it can start to spawn new machines to produce this sort of tree structure. And then the execution was a sequence of activations. So an activation starts from an active state. It's a sequence of states, where a state includes the tape information and all of that, from active to inactive. So at some point the machine deactivates by sending a message to another machine. Inactive. I shouldn't write while speaking, I confuse them. So an activation was a sequence of states, starts from an active state, and then the machine sends a message, and it can either invoke a new machine in doing so or send one to an existing machine. In either case, the current machine is deactivated. So that's an activation, and then an execution is a sequence of activations, potentially of different machines. Okay, so we went through the example as well of how this works, explicitly spelling out the tuples. And now we understand an execution of an interactive Turing machine, interactive TM. Okay, so now we look at protocols. So the idea of the protocol was that we have an adversary and an environment, and also the protocol itself that is trying to achieve some property despite the interfering. So recall that we defined a special case of the identity. So an identity of a Turing machine of an ITM was just some natural number, but now we say there's a protocol ID and a session ID. Sorry, there's a party ID and a session ID. So this was to handle the case that we discussed a few weeks ago about running multiple zero-knowledge proofs in parallel. These would be different sessions. And then we argued that under a more naive definition, we argued that the two sessions running in parallel could share information and break the security. Okay, so this is our starting point. And I'm now going to define an execution of a protocol with an adversary and an environment. I'm going to clear this board so that I can write this down. Okay. So let pi, A, and E be interactive Turing machines. Now, the idea of pi is that it might involve several different machines, right? Or different parties. So this is going to be somehow an initial party that will spawn or that will invoke the others. And then the A was the environment. Sorry, the A was the adversary. And the E was the environment. Okay. So an execution, and we will write this as exec pi ae, parameterized by k and z of the protocol with the adversary A and the environment E. What it is we take an execution of the ITM and the environment, just like in the simpler case that we discussed at a higher level, the environment orchestrates everything. It is the first thing that gets control, it is the first thing that gets external input. And recall that an execution had a control function, which says which parties can talk to which and so on. I'm going to call this C pi A exec, and I'm going to define this control function in detail to specify what the execution is. With input Z, so Z, the parameter Z is the input, and security parameter K. So K intuitively represents the length of the key, and we're going to do some kind of asymptotic argument in terms of K, where we define C as follows. Okay, so we have an execution of the environment with a particular control function on input Z, and we're all parameterized by some security parameter K, which is going to become asymptotic. And our control function is defined like this. So the first case is when the environment is writing a message. We specify what the environment is allowed to do. So E can write to any ITM with the same session ID. So the environment can write to any ITM that's in the same session as it. Okay. The code of the ITM is set to pi. So in other words, the environment invokes the protocol as part of the startup. And E can choose, any sender ID. So the environment can claim to be whatever it likes. And this is to capture this idea of external identity. If the party ID is, we're going to choose a special symbol, diamond, to represent the adversary. And the code is then, instead, it's set to A. Okay, so the environment gets initial control. It can set up it can send a message to the protocol. It can also send a message to the adversary, and the control function ensures that's all it's allowed to do. It can only communicate with the protocol and the adversary. And the environment is also, this condition says the environment fixes some session ID. And it's called the test SID in the paper, but we don't really reference that later. So the idea is the environment is run, it starts a session, it can invoke the protocol, it can invoke the adversary, and it's only allowed to talk to those particular machines. It can't just do arbitrary behavior because that would be a bit silly. Questions so far? I'm going to go on to define what the adversary and the protocol can do in a second, but I want to check that you're with me. Great. Okay, so now we define what the adversary can do. Okay, So the adversary, recall that we have this input, output, and backdoor tapes. The backdoor tape represents the adversary's actions, so the adversary should only be allowed to write to backdoor tapes. So the control function only allows messages where the tape that we're writing to is set to backdoor. And forced write is always set to 0. So you'll recall that means the adversary cannot invoke new machines. In particular, it can't create a straw man version of the protocol that it communicates with. That wouldn't make sense. The adversary is only allowed to communicate with the protocol that already exists. Okay? And now we discuss what others can do. So there's a few conditions here. Others being machines that are generated as part of the protocol. Pi. So reveal sender ID must be set. In other words, the protocol has to be honest about who it is. Is 1. And if the protocol is writing to A, it has to use the backdoor tape. And forced write has to be 0. So in other words, the protocol can't spawn a different adversary. And the receiver code is unspecified. So if it's communicating with the adversary, it doesn't get to dictate what the adversary can do. Okay. So recall that we had this idea of main machine, which is pi. Maybe I should have mentioned this above, my apologies. The initial party equals the main machine, the one that is initially invoked by the adversary. So if the main machine is sending, and the target tape is output, subroutine output, but I'm shortening this. And the receiver doesn't exist. So the situation that I'm matching here is the main machine is sending output to a machine that hasn't already been created. What this corresponds to is the main machine sending output to an external identity, to the environment, because it's giving output and it's not giving output to a machine that it invoked itself. So it must be giving output to the environment. The message is, so in this case, the message gets sent to E. Okay, and finally, I want to define what the execution actually is as a variable. It has some value. The value of exec pi a e k comma z is the output tape of E, whoops, at the end of execution. Okay, so this definition is a lot of words, but it's sort of just codifying what we already intuitively understand, right? We have some fixed input Z, and this is eventually going to, we're going to parameterize over all possible values of Z to make sure that no input can break the protocol. We've got some asymptotic parameter K, And then we take the environment, we execute it in such a way that it can only talk to things with the same session ID, it can only create pi or a, and if it's talking to pi, it can choose to impersonate whoever it likes. And then the second rule says the adversary can only communicate with the backdoor tape and it can't create new machines. And then for pi, okay, pi is allowed to invoke new machines, but the main machine itself, pi, if it gives output, then it has to give that to the environment. That's all we're saying here. And then finally, when we talk about like what the value of the execution is, that's just whatever's left on the output tape of the environment. And it suffices, as we will later discover, it suffices to consider that as a single bit. All right, so now we know what an execution of an ITM is, and now we know what an execution of a protocol, an environment, and an adversary all together is. Any questions? I take this as perhaps a no. Fabulous. Okay. So now we can finally define what protocol emulation is. Okay. So I am going to again take a small departure from what the paper says. It defines emulation with respect to a fixed identity class, which will be useful later, but for the time being, I think this is an unnecessary complication. So now I'm going to define finally what UC emulation actually is. And we want a little gadget first. I'll call this definition 2 now. So we want to talk about families of probability distributions, right? Because we want to quantify over all security parameters and over all inputs. So I define a little gadget. The paper calls this a probability distribution ensemble. I have no idea if this is a standard definition. It's called a PDE. Sorry if you do differential equations. It's an indexed family. Of probability distributions. X, which is x of kz, our parameterizations, where the security parameter ranges over the natural numbers, and z ranges over all binary strings. And we say that two PDEs, x, y, and the distribution will be over 0, 1. We will revisit this in the theory later. The execution, it turns out it's sufficient to only consider environments that output 0 or 1. We say they are indistinguishable. And we will write x approximately equals y if for all C and D we have k such that for all k0, we're doing some classic analysis, for all k, it should be k0, I apologize. For all k greater than k0 and z of length at most k, we have that the outputs are the difference in the probability that we output 1 sorry, I messed up. It is in fact length k to the d. So the idea is the input is polynomial in k, right? The length of the input is polynomial in the security parameter. And then we're going to ask that the difference in the probability that x and y spit out 1 is negligible in k. Less than k to the minus c. Okay, so we have an index family of what obviously is going to be executions. And we say that they're indistinguishable if given an input that is polynomial in k, the difference in probabilities of outputting 1 is negligible in k. That's all that's going on here. Okay. So now we can define what we really care about, which is UC emulation. And so an ITM pi UC emulates another ITM phi if for all probabilistic polynomial time, which we haven't defined yet, but trust me, we'll get to it, ITMs A. So for all efficient adversaries, there exists a efficient simulator such that for all efficient balanced environments, balanced is a question we'll get to in a second, the ensemble exec pi a e is indistinguishable from exec phi s e. Okay, so UC emulation is now defined in terms of given any efficient adversary, we can produce another efficient adversary such that no matter what environment we're in, the execution of pi looks like the execution of phi. Now we have two questions. The first question is what does efficient mean? How do we define polynomial timeness for this? What does balanced mean? Balanced is a condition related to the technicalities of of efficient ITMs that we'll get to. And then also, okay, we have this definition, but we want to prove a composition theorem. So I'll write these questions up on the next board. What is...
Sorry, Eleanor, the camera got stuck on these proof trees, so you might have to walk a bit closer to the board.
Oh, did it snap to... I see.
Yeah, there it is.
Is it good now?
Yep.
We're here. So what is a PPT, or efficient interactive Turing machine? This is far from clear. And then how do we state and prove a composition theorem? So perhaps if you just focused on the mathematical deal of what's going on, you might say, oh, well, okay, the relation defined of indistinguishability, of course, this is a transitive relation. This is, you know, we could show this, and isn't that the composition that we need? But that would fall into the trap that we mentioned a few weeks ago that only handles sequential composition. What we want to be able to do is to swap out a piece of a protocol with another piece of a protocol, and then say that overall the thing is secure. In particular, if I have, some enormously complicated, I'm having Palm issues again. Okay, so I have some enormously complicated protocol that I'm calling pi, and then it has, as part of its assumption, it uses some piece. I call this phi. And then pi assumes phi is a perfect crypto system, which of course doesn't exist, right? We can't construct a perfect crypto system that isn't the one-time pad. Then what we want to be able to do is take an imperfect part, an imperfect crypto system rho, and swap out the assumed perfect part of phi with rho, where rho is indistinguishable from perfect. And we want to maintain the security property. So if pi is indistinguishable from capital phi, then we should be able to swap out the assumed perfect crypto system with something else that is approximately perfect and still be indistinguishable. So this happens all the time in real world protocols, right? When I connect to the internet, when I connect to a web server using HTTPS, I have at least two separate parts. First, I have a key agreement procedure where me and the server exchange some messages and we agree on a secret key. And then I have a symmetric cipher that encrypts our messages with that shared key. Now, separately, we show that our symmetric cipher, given a uniformly random key, is indistinguishable from a perfect cipher. And then we show also that our key exchange produces a key indistinguishable from perfect. Then I should be able to swap out one part. I should be able to put these two together and get an overall perfect system, right? So TLS, we could prove that TLS or HTTPS is secure, assuming perfect key exchange, assuming perfect cipher. Then we prove that we have something that is indistinguishable from a perfect key exchange and a perfect cipher, and swap out these pieces. So this is going to be the major difficulty, really interrogating, okay, given all of these different moving parts, can we do this swapping out, and does it make sense? And in particular, transitivity of indistinguishability does not suffice. Okay, so I'm not going to... Which example, sorry? Yes, that's a good question. I don't know if TLS has ever been formally put into the UC framework because TLS is super complicated. I know that some simplifications of it have been put into frameworks. I think it's been done for UC. It's certainly been done for it's certainly been done for a version of constructive crypto, which is what I work on. The problem is that it's so enormously complicated that you kind of have to make simplifying assumptions for it to work, or for it to be workable. So the answer to your question is sort of. Yeah. The main complication with real-world TLS is you have all of these different cipher suites that you can choose from, different signing algorithms, different key exchange protocols. Yeah. But this general approach in our nice Platonic abstract crypto perspective, this really does work. You can prove that swapping out pieces maintains security in the UC sense. And that's what we'll work on later, because it will take more than 20 minutes to go through. But now we're going to revisit, for the rest of today, we're going to revisit this idea of efficiency. And it turns out this is actually not too difficult to beat into shape. Okay, I go back to the first board. So just figuring out how an interactive Turing machine can be efficiently handled is not straightforward, because, okay, we have this nice little definition. Given a function t, a Turing machine, and a normal Turing machine is t bounded if given input of length n, it halts after at most t of n steps. So if I were to, so for example, I could prove that a Turing machine is polynomial time if I can prove that it's t bounded for all polynomials. Good. Now I want to extend this to an interactive Turing machine, and sort of a naive first approach might be to say, well, if every activation in the execution is t bounded, then maybe the whole thing is in some sense efficient or polynomial timed. Unfortunately, this doesn't work, and maybe it's not entirely surprising how. Essentially, you have two ITMs that play ping pong in a sense. They send each other messages, and if t is not the identity function, each time it activates, it can increase this length, right? So they can activate each other with increasingly long messages, and then we end up with an unbounded amount of resources. So we can't just assume every activation is t-bounded. And this is one of the segments of UC that has gone through the most revision. There's lots of tricky gotchas in defining efficiency. And the way that we're going to do this is every message that an ITM sends contains what's called import. And this is some resource, some abstract resource that defines how much a machine can do. Okay. So an ITM's budget, how much resources it's allowed to use, in some configuration, it's going to be the sum of import received so far. I maybe highlight this as a keyword. Import. In practice, this is going to be like, the import values are going to be natural numbers. So it's the sum of import received so far. So all of the import that it's received in messages minus the import it's sent. So the idea is to avoid this ping-ponging problem by saying, well, the budget has to be non-negative. Okay. So now we can define what polynomial time is going to mean in terms of these pieces. 7, that's not number 7 in this lecture. Definition 4. Okay. So let t be a function as above. And we say an ITM mu is locally t-bounded if in all execution prefixes, so we're in an execution and then we take a prefix of this execution and examine it. Of systems of ITMs. Remember, a system of ITMs was an ITM with a control function. All machines with code mu, because there could be multiple different identities with the same code, have taken at most t of n steps where n is their budgets. Okay, so locally t-bounded means that it has not taken more steps than allowed by its budget, by the amount of input it's received minus the amount it's sent. And now we're going to recursively define t-bounded in terms of this. So locally, the idea behind locally t-bounded is ignoring any communication that's happened maybe to reactivate it. It hasn't taken more steps than its budget allows it to. Okay, so a locally t-bounded ITM that never invokes an ITM is t-bounded. So if it's locally t-bounded and it never creates new instances, then it is definitely t-bounded. And then a locally t-bounded ITM that only writes to t-bounded ITMs is also t-bounded. Okay, and an ITM is probabilistically, an ITM called mu is probabilistically polynomial time if there exists polynomial P such that mu is p-bounded. Okay, so if you never invoke a Turing machine, you are t-bounded, and if you only write to t-bounded Turing machines, then you are t-bounded. So we end up with this recursive construction where as long as you only end up writing to locally t-bounded machines, you are yourself t-bounded. And then the question is, okay, well, this definition, how do we know this is the right definition somehow? How do we know that we don't have any cases? And we're going to justify this by saying, if a machine is t-bounded, where t is so-called super additive, then we can simulate it with a polynomial-bounded, non-interactive Turing machine with just one. And we're going to finish off today with this proof. Theorem. let t be increasing and super additive. That is, for all n and m, t of n plus m greater than or equal to t of n plus t m. So let us take a system with an initial machine and a control function. If I is t-bounded, and we can compute the control function in time t of stuff, depending on what the message is going to be, then an execution can be simulated on a standard TM in big O of t of n times t of big T, maybe the brackets are confusing, times little t of big T of n. There's a small caveat here where we do not allow the control function to increase input. Okay, so I'm going to prove that I can simulate stuff, assuming that the control function doesn't increase the input. And the idea is, okay, well, if I can simulate it in polynomial time, then it is, in some sense, itself polynomial time. And this is the justification for why this definition should make sense. Okay. So, claim the number of configurations. Remember that an execution is a sequence of activations which is a sequence of configurations. In an execution of IC is at most T of n, where n is the initial input. And this is going to justify that our definition of T-bounded makes sense. Okay, so the machine starts with some input, it can give it out by sending messages, and that uses up its own input. So, to prove this, I'm going to call MI the set of ITMs that were active at any time before the ith configuration, and given a mu in MI, we'll call its budget immediately before that configuration n mu I. Okay, so since I is T-bounded, for every mu in MI, mu is also T-bounded by the recursive definition of T-bounded. And now we can do a little calculation. So the configuration we're up to, it's the sum over all machines of the steps taken by mu. Which is, by definition of t bounded, less than or equal to t of mu ni. Sorry, yeah, n mu I. Which is, because of superadditivity, I can take the t out. Which is itself less than or equal to t of n because of the restriction of the budget, right? It can't possibly take more steps than it was allowed to by being given import. So the total number of steps is always less than t of n, where n is the initial import. Okay. So we've shown that the number of steps we've taken is less than or equal to t of n, and now all we have to do is describe how we're going to simulate the execution, which I will do over here. So a Turing machine, I'm starting to run out of letters, I'm going to use lowercase m, will write all the configurations of the execution of the system IC, on its tape, and it accepts if the halting configuration, remember that it's t-bounded, so it has to halt. And it accepts if whatever configuration I ends in is accepting configuration. Okay, how much time can this take? So the overall time is t of n plus the time spent evaluating the control function. So there are I configurations, and I is less than or equal to t of n, and t is superadditive. That was the claim that I made just before. And then whenever a message is sent, it also has to evaluate C. And it evaluates C for each of the I less than or equal to t of n configurations. Okay. And since C is evaluated at most t of n times, we have t of n, big O of t of n times little t of t of n. Yay, we did it. Okay, so the big picture argument is that we have a bound on how many configurations can possibly happen, and by simply just writing them out, which involves evaluating the control function t of n times on t of n times on a string that is itself at most t of n pieces long, then we can evaluate it on the thing, and because polynomials are closed under these operations, we end up with a polynomial time Turing machine. Now, there's one last piece of the puzzle, which is that technically the protocol could bump up its, when we run an execution, the protocol could bump up its import by sending some to the adversary, and then we'd end up with the adversary running too many steps. So we will.
Sorry, could you say that again? I'm not really clear on how the import is managed. I mean, so this is something that lives outside of any machine, and
yeah. So it's we augment the messages that we send with an import value, and we don't allow import to be sent that it can't afford. That would destroy its budget.
Okay. All right.
And in particular, I have to check the paper because I did not remember to write this down. I will be with you in 1 second. Yes, so we disallow the protocol sending import to A for simplification. This doesn't mess up the model because any messages sent to the adversary on the backdoor tape are modeling artifacts. The one more key condition is this balanced thing. So this is sort of patched into the paper to fix a certain class of ways that can go wrong. In particular, the environment could send lots of import to the protocol and almost none to the adversary. And then the UC emulation becomes too weak. The adversary might not even be able to interact with the protocol at all, and that becomes really easy to satisfy the existence. So balanced says if the environment gave n1 ... n1 ... nk to any k ITMs, it also gave to any k ITMs not including the adversary, then it must have given at least the sum of these to the adversary. Okay, so the idea is the environment has some initial amount of import. When it sends messages to protocol machines, it also sends some amount of its import to the protocol machines. Again, when the protocol machines talk to each other, they send some amount of import to each other. And we have this budget condition where it can't just go everywhere. And then we have this balancing, which basically just says the environment can't starve the adversary. Otherwise, we would end up with a definition that's too weak. Okay, so the general idea here is that we've shown if the machines obey these conditions, then they can't do arbitrary things by messaging each other because that would break the budget. And furthermore, if T of n satisfies this superadditivity condition, then you can simulate it on a polynomial time regular Turing machine, which serves to justify why we interpret this as efficient. It's a different notion of efficient to a regular Turing machine, but this theorem aims to argue that it is, in some sense, comparable. Maybe at this point I comment that the crypto standard where we say, okay, polynomial time counts as efficient. I mean, this is itself arbitrary, right? Certainly because we don't have P versus NP decided, it could be that polynomial time is not really a meaningful distinction to make. So in some sense, we could choose whatever notion we liked for the interactive case, And this theorem tries to give a sense of how it relates. Does that make sense? Yeah, so as I said, this is sort of one of the areas of UC that has gone through the most updates because it's actually very difficult to define a coherent notion. And this is the one that we've settled on after nearly 20 years, or more than 20 years even. Okay. Yeah, maybe it would be nice, maybe next time I'll try to give a more concrete example of how this behaves. Because this is interesting, and also so there's a lot of subtleties that it tries to avoid. So maybe we can interrogate that next week, next seminar, before we go on to arguing that we have the composition properties that we want. Great. Any general questions?
Not from me. Yeah, thanks a lot.
Rohan?
No, sorry, not from me, but thanks for
Okay. Sorry, I cut you off there, Dan.
No, I think I don't really have a question. I have to process this definition, but it's certainly interesting to see it naturally arise that somebody has to think hard about imposing polynomial time constraints on a processing system made up of multiple Turing machines, and that this is an interesting idea, and it appears naturally here. So I find this quite fascinating, but I think I'll have to think about it and ask you next time.
Yeah, I think that's what we'll kick off next seminar with. We'll revisit this and think about it a bit more. Great.
Thanks, Eleanor.
All right. Have a nice evening. We'll see you next time.
Yeah.